In the cosmos, it seems there are still unresolved mysteries, and our understanding of how rings form around planets and other celestial bodies may be incomplete. A recent discovery of a ring system in our solar system underscores this enigma. A team of astronomers presented groundbreaking research in the journal Nature, announcing the detection of a ring system around Quaoar, a trans-Neptunian object classified as a dwarf planet. Trans-Neptunian objects, located in the outer solar system beyond Neptune's orbit, constitute a vast population of distant worlds. Among them, dwarf planets Pluto and Eris stand out, while Quaoar ranks 7th in size, with a diameter of 1,121 kilometers, roughly half that of Pluto. Discovered in 2003, Quaoar resides in the Kuiper Belt, a region populated by numerous icy and rocky bodies. Quaoar even possesses its own moon, Quaoar, which is approximately 160 kilometers in diameter. In an article published on February 8, astronomers reported that Quaoar possesses rings. This is not a unique phenomenon in the solar system, as rings encircle Saturn, Neptune, Uranus, and Jupiter. Additionally, a ring is known to exist around the dwarf planet Haumea and the asteroid Chariklo, located between Saturn and Uranus. However, Quaoar's ring appears to be peculiar. It is situated at a significant distance from its parent body, effectively twice as far as modern astronomical theories predict. This challenges existing understandings of how rings form around astronomical objects. Observing trans-Neptunian objects, even large ones, presents a complex challenge due to their remoteness. Quaoar orbits the Sun at a distance nearly 44 times greater than that of Earth from the Sun. To study these small and distant objects, astronomers employ various methods, including occultation. Occultation occurs when one object passes in front of another from an observer's perspective. A solar eclipse, where the moon partially or completely obscures the Sun, is a striking example. These events provide valuable information to astronomers. For instance, the chemical composition of Pluto's atmosphere was determined long before the New Horizons mission. In 1988, when Pluto passed in front of a star, astronomers conducted a spectral analysis and detected nitrogen in the dwarf planet's atmosphere. In 1977, by observing Uranus pass in front of a star, scientists discovered the planet's rings, noting a 5-fold dimming of the star's brightness instead of the expected single dimming. Astronomers used a similar method to study Quaoar. In a series of observations from 2001 to 2021, they investigated the dwarf planet as it passed between Earth and several distant stars. Detecting the slightest changes in brightness required a highly sensitive telescope. This instrument turned out to be the Quaoar Space Telescope, launched by the European Space Agency in 2019 to study the sizes of already discovered exoplanets. Analysis of data obtained with the Quaoar telescope revealed that, in addition to the primary dip in background star brightness, 2 smaller dips were observed. These dips occurred before and after the main occultation, leading researchers to conclude the presence of a ring around Quaoar. Prior to this discovery, it was believed that rings could not exist at such a great distance from their parent body. Located approximately 4,100 kilometers from the dwarf planet's center, the ring is so far out that Quaoar's gravity should not be able to keep its material dispersed. Instead, under its own gravity, the material should have coalesced to form another moon around the dwarf planet. Quaoar's ring violates what astronomers call the Roche limit. The Roche limit is the distance at which a celestial body's tidal forces will tear apart a satellite orbiting it. Within the Roche radius, material will disperse and form rings. Beyond it, it will coalesce. Until recently, all known rings in the solar system, including those of Saturn, Chariklo, and Haumea, were located within their respective Roche radii. Quaoar's rings, however, appear to be the first to violate this limit, which has surprised the scientific community. A group of researchers currently studying Quaoar's unique ring system has developed a computer model of the phenomenon and put forth several hypotheses to explain its unusual characteristics. One theory suggests that Quaoar's rings could be the remnants of a former moon that was destroyed by a collision with a large celestial body. However, scientists note that even after such a catastrophe, the debris should have recoalesced under gravity within a relatively short period, approximately 10 to 20 years. Therefore, it seems highly unlikely that the observation of Quaoar coincided with the period of these rings' existence after a hypothetical collision. As an alternative explanation, it is considered that the particles making up the ring are covered with a solid layer of ice. This could lead to more energetic collisions and rebounds, preventing them from sticking together. Another possibility is that the particles are moving at high speeds, which also prevents their consolidation. It is hypothesized that the gravitational interaction between Quaoar, its moon, and objects in the ring might be the cause of such velocity. Despite these hypotheses, none have yet received conclusive confirmation. Therefore, scientists intend to continue observations of Quaoar to gain a more complete understanding of this unique ring system. Additionally, plans are underway to study other similar objects in the solar system to assess how common such ring structures are in space.